This video is a review of the third law of thermodynamics and absolute entropy chapter in the chemical thermodynamics playlist. The temperature dependence of entropy is determined by its partial derivative with respect to temperature, and at constant volume, that is the constant volume heat capacity divided by temperature. At constant pressure, its dependence is the constant pressure heat capacity divided by temperature. So if you have some temperature range where there is no phase transition, then the entropy at a given temperature is the entropy at 0 Kelvin plus the integral from 0 to that temperature of constant pressure heat capacity divided by temperature, integrated with respect to temperature. So we need to know what this entropy is at 0 Kelvin for a given substance. And the third law of thermodynamics says that the entropy is 0 at 0 Kelvin for a perfect crystal. So a perfect crystal is one which has no defects and has a regular perfect lattice structure. The entropy which occurs during a phase transition, which we cannot go across in this type of integral, is equal to the transition entropy is the transition enthalpy divided by the temperature of the transition. So the transition enthalpy is the amount of heat that is absorbed by the system in a constant pressure process, and we take that and divide by the temperature of the phase transition. The Debye T cubed law tells us that the heat capacity of a solid as we approach 0 Kelvin is going to be proportional to the temperature cubed. So as we get to very, very low temperatures, the heat capacity is proportional to the cube of the temperature. And this means that the limit as the temperature goes to 0 of the constant pressure heat capacity is 0. So at absolute Kelvin, the absolute 0 Kelvin, the heat capacity of any substance is going to be 0. So any input, any infinitesimally small amount of heat which is absorbed in the system is going to result in the temperature going beyond 0. We can determine enthalpy. We can determine entropy on the absolute scale experimentally by calorimetry, or we can calculate it through the use of statistical mechanics. If we use calorimetry, what we need to do is measure the heat capacity of the substance at every temperature, going down as close to absolute 0 as possible, up to whatever temperature of interest we have. And then we measure these values, and you can plot the constant pressure heat capacity divided by temperature as a function of temperature. And you numerically integrate this value, and then add in whatever entropy of transitions you get from your enthalpy of transition. And through that process, you can calculate an experimental result for what the absolute entropy is of a given substance at a given temperature. We can do this through statistical mechanics if we can calculate what the partition function of the substance is. So the entropy is equal to the Boltzmann constant times the natural log of the partition function, plus another term, the Boltzmann constant times the temperature, plus the partial derivative of the natural log of the partition function with respect to temperature, those being taken at constant number of particles and volume. And then there may be some discrepancy between what you calculate statistically and what you measure calorimetrically, and this is called the residual entropy. The residual entropy is the difference between what you calculate in statistical mechanics and what you measure in experiment, and generally statistical mechanics has a small amount of entropy which is greater than that which comes from experiment. And this is called residual entropy, and it comes from there being an imperfect crystal. So the entropy is only 0 at 0 Kelvin if the crystal is perfect. But if you have carbon monoxide, for example, there's a very small dipole moment, giving energetic preference to these dipoles being anti-aligned throughout the crystal structure. But this energy preference is very small, and the crystal often forms without a perfect lattice structure, and this gives rise to residual entropy, which is observed in some substances where you have this kind of imperfections in your crystal at 0 Kelvin. You can define entropy for a chemical reaction. The standard entropy change of a reaction is equal to the sum over all the products of their stoichiometric coefficient times the standard molar entropy of that product as determined by experiment or by theory, minus the sum over all of the reactants of their stoichiometric coefficient times the molar entropy of that given reactant.